Okay. Right. Can you see the slides now? But okay. Right. So yesterday we have discussed a little bit on the characterization of the wafers after diffusion process. So when you do fabrication, after every single step, you need to characterize the results. So you need to know what do you get after the process. So the same goes to our previous processes as well. So thermal oxidation, lithography, etching. So each of these process has its own respective characterizations. So if not one, then maybe a couple of characterizations that need to be done on the silicon to make sure that you get what you plan to get, right? For example, if you talk about thermal oxidation, you get the right thickness of the silicon dioxide, the right density, the right quality of silicon dioxide. If you talk about lithography, then of course we've discussed about DICD, the profile, the LER, uniformity of the patterns produced on the resist. And then if you talk about etching process, then it's the FICD. And then we also monitor the DIFI bias, right? The difference between the CD after etch versus CD after lithography. And some of the stuff as well, including the defects. Defects are basically done after every single step, every single process throughout the 2 or 3 months cycle time for each product. Uh, so the same goes to the diffusion. When you manage to diffuse, when you successfully diffuse your channel or your emitter or your whatever you call it, according to your device. So you want to know how much you have diffused into the silicon in terms of the junction depth, in terms of the doping profile, surface concentration. So, and they basically can be characterized by a couple of techniques that we have discussed today. So, for example, you can use ECV to measure both doping level and junction depth. You can also do SIMS as the alternative to ECV. Um, by you can also measure both the doping level and junction depth. Uh, Hall effect can also be used, but it's rarely used in production line because it can only measure the doping level, but they are more interested in the doping level and junction depth. So Hall effect is more to lab scale, but if you talk about production scale, then it's going to be ECV and SIMS, right? And another one, the simplest one is a 4-point probe. You can also include here. Oops, why is it not? Right, so you can also include here 4-point probe or 4PP, 4-point probe. So where you have 4 points, 4 needles, 2 for voltage, 2 for current, to measure the shear resistance, resistivity of your surface. So in this case, after diffusion, you can measure the shear resistance or resistivity of the diffuse layer on top of your silicon, right? So this is one of the parameters that we measure after the diffusion. So we measure shear resistance. It can be done by these characterizations. So we have discussed this bulk last time when we talked about physics. I think it's in the carrier transport phenomena as well, if not mistaken. So this is a set of basic equations, if you like. Well, you can see here if you have a block of diffuse layer, for example. So you have current going through. You have a length of the layer here L, and then resistance is equal to rho L over A, where rho is the resistivity, L is the length of the channel, if you like, or the diffuse layer, and A is the area, where area is equal to the times thickness of the channel. So WT, A is equal to the WT, and then you can just replace whatever you have here into R rho L over T, and then that will give you RS L over W, right? And RS, or sheet resistance, here can also be simplified as resistivity over thickness. So if you know for example, if you talk about channel formation on MOSFET, if you know the thickness of your channel, right? If you know the thickness, so let me re-sketch. So that's your gate, and this is the gate aux, and this is source and drain. Okay, for example, if you have diffused this layer, for example, you know the thickness of this. This is the T that we're talking about, right? So you measure 4-point probe. So I put the 4 points on the channel now. So assuming these are the needles, 1, 2, 3, 4, measured by 4-point probe. So you measure, and then you're gonna get the resistivity, right? Resistivity here in this case is actually equals to, the resistance can be calculated by resistivity over thickness. So if you know the thickness, you know the resistivity, you can you can know your sheet resistance in terms of ohm per square. So normally we write it like this: ohm per square, or some condition we also write ohm per square box, right? So the value of your sheet resistance will depend on your device. Well, if you talk about, for example, if you talk about solar cell, if you diffuse an emitter, I'm going to go through this one later on when we talk about fabrication of silicon solar cells. When you diffuse an emitter on, for example, a P-type silicon wafer, then you diffuse your phosphorus, then the typical thickness of the N-type layer is usually around 100 to 200 nanometers, so N-type. So normally in the industry, they are targeting somewhere around 100 ohm per square, more or less now, of the N-type diffuse emitter in silicon solar cell. So if you talk about other devices, then we are talking about other values of the sheet resistance, of course, right? So, and this sheet resistance, it plays a crucial role to determine the conductivity of your diffuse layer, whether it's a channel or it's a blanket diffuse layer. So if you get a very high conductivity in that layer, so you want to have a very low level of sheet resistance, right? So maksudnya resistivity of the layer is also low and sheet resistance is also low. So what low sheet resistance means is that your carriers, electrons in this case, can pass through the channel with minimal resistance. Okay, so that's what it means by low sheet resistance. So maknanya you punya carrier, kalau you extract, if you're talking about p-n junction, for example, if you extract electron into n layer and holes into p layer, for example, then we're talking about the journey of the electrons within the channel or within the dope layer. So if you're talking about low sheet resistance, then it's a lot easier for the electrons to pass through to get to the metal contacts, right? Because last time that we're not going to be able to place metal contacts everywhere, blanket on the surface. In most cases, in some cases, yes, you can, depending on what device are you talking about. So where you put your metal contact sparsely on the surface, so you have like every you have a periodic array of metal contacts. So that means some areas of the surface do not have the metal contacts. So in that case, if the electrons are extracted somewhere there where the metal contacts are not located, so they need to travel through some distance laterally or horizontally through the layer to get to the nearest contacts. So the nature of electrons traveling is that you will be extracted at the nearest metal contacts. Kalau dia tak jumpa metal contact, dia akan cari yang the next nearest one, right? So while looking for the next nearest one, or while traveling to the next nearest one, so it will have to go through some resistance in the layer. So in this case, we're talking about the diffuse layer. So if your shear resistance is lower, then it's going to be a lot easier for them to travel through the layer to get to the nearest contact. And it's always the best to have lowest shear resistance in all devices, because there are different issues in different device. Okay, if you talk about a MOSFET, maybe it's correct. Maybe you want to have as low shear resistance as possible for your channel formation. But for solar cell, there are other concerns. We have learned in 386 last time, so that's why it's crucial. Kita dah belajar when you dope your layer with heavy doping, can to be able to get low series resistance, you need to dope your layer with heavy doping. Kalau you dope heavily, for example, you go for high 19s per cm cube, then you will end up with low shear resistance. If you go to 1014, 1015, you're going to end up with high series resistance. So the good thing about going to heavy doping is you will improve the channel conductivity by reducing the resistance. But going to a very heavy doping, if you talk about higher than 1070, your device or the layer is subjected to Auger recombination. Kita dah discuss recombination last time kan? Masih ingat lagi berapa recombination type that we have? Can you run that? Berapa recombination kita ada dalam semiconductor device? 3. Okay, what are they? Auger is one. Tulis kat sini. Auger is one. Auger happens when you go for SRH, Shockley Reed Hall. Auger happens when you dope your layer, your device beyond 1017 typically per cm cube. So kalau you go for heavy doping lah, Auger. Then you're gonna have SRH if you have defects in the layer, and then the third one is obviously what? The third one? Kita baru discuss dengan OSRAM minggu lepas kan? So what's the third one? That's the most important for OSRAM. What recombination they want to have? But come on. SRH, OJ, and huruf R. Itu takkan dah lupa. Radiative, right? Radiative. So radiative recombination. You want to have radiative recombination in optoelectronic devices. Specifically emitting devices, light emitting device, LED, and lasers. You want to have radiative recombination in the device. You want to induce radiative recombination in the device. If you can recall, Dr. Fabian had a checkup last week. LED is the opposite of solar cell, right? In solar cell, you absorb the light in order to produce current and voltage or electricity, right? On the other hand, in an LED, you supply the current and voltage, of course, in order to induce light emission, right? In order to induce light emission. So it's a completely opposite mechanism for solar and LED. And in fact, you can find this statement online as well. A good solar cell is a good LED. Kita tengok what does it mean by a good solar cell is also a good LED, or a good LED is also a good solar cell? You try to figure that out, right? Who knows? It's gonna come up in your test too, right? So what does it mean by a good solar cell is also a good LED? Is vice versa. A good LED is also a good solar cell. Apa maksudnya? Okay, so we have OG recombination. When you dope your channel, your emitter ke, your blanket layer ke at a very high doping, of course, it's going to improve the conductivity. It's going to reduce the heat resistance, but it comes with enhanced recombination as well. So remember that when you incorporate impurities into the silicon lattice, in some cases, you may also induce formation of defects. So defects are SRH recombination centers. So you will probably end up with more SRH recombination as well that will affect your ideality factor of your PN junction, right? So that's why nanti kita akan discuss later on in solar cell. You want to go for low shear resistance, but then it cannot be too low because of some reasons, right? So if you look at solar industry, the sheet resistance that I wrote down here was actually around 80 ohm per square a couple of years ago, like the one that they're doing now doing in Jinko Solar, JA, and some other silicon-based solar cells. But this value is actually increasing over time. So they want to go gradually to 100 ohm per square, and then maybe in the next couple of years, 110 ohm per square, 120 ohm per square, which is the opposite of what we're trying to achieve. So, and there's a reason for that. Tapi nak explain tu kita kena explain lebih kepada solar cell lah. I'm going to go through later on hopefully. But generally you want to go for as low shear resistance as possible. But for solar cell, diffuse layer, you want to go gradually higher over time. And that's the reason for that, right? Kalau you nak tahu, you boleh check dalam. Kalau you nak tahu sekarang, or a bit later on, you can check it out on ITR PV roadmap. International Technology Roadmap for Photovoltaics. So every year they akan publish and they akan tunjuk map for PV in general, storage, PV technology, emerging materials, silicon based, where industry is going. Kalau you ada interview untuk silicon solar cell selepas ni, silicon solar cell punya company, I advise you strongly to look into ITR PV document and try to look into the roadmap of the industry so that you understand where they are heading now and in fact where they are now, right, to the future. Okay, so kalau you ada interview untuk internship ke job ke whatever for solar cell industry, particularly silicon, then have a look into this document ITR PV. Right, so nanti saya akan explain kat you kenapa for silicon solar cell for diffusion process we don't want to go that low because we have some other concerns which is not applicable for IC fabrication. All right, so okay, doping system we've discussed this one before. You can also watch this on YouTube. Well, the doping process can be carried out by various techniques. So the one you can watch on YouTube is actually by POCL or POCL3, phosphorus oxychloride. So where we bubble the POCl3 precursor and then we use a nitrogen gas to send the vapor into the furnace, into the boat, into the quartz, triple stack, industrial scale, and then start diffusion process at high temperature in the region of 900, 1000, depending on the process requirement. Instead, we can also do that by some other methods. So method yang saya sebut tadi tu dan saya tunjuk tu is the gold standard lah, gold standard method. You can also do diffusion process by another technique. You can also use spin coating, particularly if you are working with silicon with circular shape, so lebih senang spin on. So you can actually spin on. If you don't use then you can also use phosphoric acid, H3PO4. So H3PO4 phosphoric acid. So what you can do is you can spray. You can just spray macam spray iron, spray, or you can in fact dispense by just like lithography process, resist spinning process lebih kurang. You can just spin or you can spray instead. Then you can send the wafers on the belt furnace and then they can be diffused in like zone furnace. And you usually have like triple zone where in the first zone you warm up the temperature, and then the middle zone will be the actual diffusion process, and then the third zone will be the cooling process. Temperature sama aja, cuma the method you introduce the precursor phosphorus tu yang berbeza. So in our previous technique we discussed about Pockle, so you bubble, you sand the vapor, but in this case you spin on ataupun you spray the phosphoric acid on the silicon and then you run the process at high temperature as well. So it can be done by spin on process as well. Okay. So this is not spin on is not applicable for talk about wafer yang bentuk square. Then it's going to be harder to spin on in comparison to wafer yang berbentuk circular ataupun spherical shape lah, right? Any reason? Kenapa kalau spin on square shape substrate, for example, square shape silicon, is harder to do in comparison to spin on circular shape wafer? What do you think? Kalau you spin on square shape, you akan dapat some stain. Ataupun you punya hujung tu akan dapat some defects lah. More defects, in fact. Any ideas? It's easier to do on circular in comparison to square shape. Anyone? Ada idea? Hazika, ada idea Hazika? Hazika ada? Tak ada. Izian, ada ideas? Kenapa susah nak spin on square shape? Izian? Write down or you can unmute. Chingwei, anything? No idea. Okay, Chingwei, go Chingwei. Ni physics lah, dia punya basic, the mechanism is physics. But I let you explore. Cuba jadi kenapa susah nak spin on square shape in comparison to circular shape. It's in the force during the spinning. So you think, kenapa force tu tak works on, it's not that it's not working, but it's not working optimally on square shape wafers. Try to figure it out. Right, and the rest of the items on this page, 3-zone furnace and everything is standard one that we discussed before. Yes, it's not going to be uniform. Yes, it's due to the force. So kalau force tu, so bila you spin, force tu dia pergi ke mana? How does it distribute the liquid on the surface? Yeah, it's not going to be uniform, but you have to look into the direction of the force while doing the spinnings. Which is the direction of the force and why does it cause the distribution of the liquid to be not uniform or non-uniform? Well, you will not have uniform distribution for one reason. Okay, you figure it out. Okay, so kat sini semua sama. Source material, you need to have either liquid or solid or gas. So, right. Another process is to also use the furnace yang sama, but then you can also use a solid source dopant. Ini kita ada dalam kita punya lab, no lab ada. Dia punya solid source ni bentuk dia macam disc, macam wafer juga. It's about 2 or 3 inch in diameter. So color je color putih. So you can either have a phosphorus source or boron source. You can also have some other dopant source in the form of disc. So solid source dopant. Solid source dopant in the form of disc lah. Dia macam wafer. Tapi dia you can arrange your wafers vertically, for example, dalam you punya quartz board, and then you place your precursor material in the front. So you have batches of wafers here. So in your quartz board, so you have batches of wafers, for example, 25 wafers. And then in the front, you can have your solid source dopant. So dekat depan sekali, and then your nitrogen is coming from the back to send the precursor material into the direction of your wafers. And then you can actually get dope as well. So konsep dia sama macam poker lah. Cuma poker we send the phosphorus vapor into the surface of your silicon. But in this case, you use solid source dopant instead of liquid, right? So boleh juga. Right, boron, phosphorus, arsenic. So these are standard depending on what do you want to use. Right, another thing that you have to be concerned with during a diffusion process is thermal budget. So thermal budget ni, okay, if you can read here, dopant will redistribute when subjected to various cycles of IC processing. Right, when you talk about, saya unshare and saya share satu website glossary. So when you impose high temperature parameters to your IC in the fabrication, so you can induce junction formation, right? So at high temperature. So thermal cycle is actually a cycle of high temperature processes imposed to the silicon or to the substrate or to your IC during the whole cycle of processing from day 1 until day 60, for example, or day 90. So every single thermal processing that you use will actually cause some level of dopant redistribution. So we've discussed yesterday about DT product, diffusivity times process time. So you have diffusivity of phosphorus, diffusivity of boron, and whatnot. And if you induce high temperature, and diffusivity is dependent to the temperature as well. So kalau you ada next subsequent high temperature processing in processes that are not diffusion, process diffusion, tapi you run high temperature, so those high temperature processing could actually cause dopant redistribution from your diffusion process. So you will probably experience, also not you, the wafers or the silicon, the ICs, will experience some sort of dopant distribution in the profile, in the layer, in the source, in the drain, to some extent in the next subsequent high temperature processing. So that's what it means by thermal budget. Okay, so saya buka satu page ni. I'll share with this page. To show you the definition of thermal cycle. Where is it already? Okay, thermal budget. Okay, so. Right, can you see the page? Nampak page website ni? Okay, good. Right, so you look at the definition of thermal budget here. So this term defines total amount, ayat dia total amount of thermal energy transferred to the wafer, during the given elevated temperature operation. So not necessarily in the diffusion process where you form your junction. It can also be during the annealing steps where you try to remove defects or something. It can also induce thermal budget or a bit of open redistribution in the profile. Proportional to temperature and duration of the process. So and look at this, it's temperature and duration. So dua-dua ni akan affect you punya DT products, right? Temperature affects your diffusivity of your dopants, and then you have some time of the process at elevated temperatures. So that will actually change your DT product to some extent. Low thermal budget is desired. So we want to have low thermal budget throughout the process cycle, but we have no choice but to induce some high temperature processes as well during the process. So in ultra small IC, so kita nak low thermal budget in ultra small IC, especially when the distance between your gate is very small and the isolation is very small. So kita nak low thermal budget in the processing to prevent dopant redistribution, right? To prevent dopant redistribution. If you're talking about fabricating semiconductor devices with microns of dimension, then maybe thermal budget tak ada issue sangat lah. Thermal budget tak ada issue sangat. in comparison to low technology node where thermal budget is very, very crucial. So kalau you talking about big dimension device, then maybe a slight change in the dopant redistribution wouldn't change the final properties of your device. But on the other hand, if you talk about low dimensional structures ataupun low technology node, then your dopant redistribution will play a greater role in determining the final properties of your device. Low thermal budget is possible even at a very high temperature if time of the process is very short. Low thermal budget is possible even at a very high temperature of the process is very short. So maksudnya you can still induce high temperature, but if the time can be reduced significantly, then you will produce low thermal budget on your IC. So, and that can be done, instead of using furnace, you can use a process that we call RTP. So RTP here is rapid thermal processing, where you impose high temperature to your ICs or to your semiconductor materials for a very short time. It can even go down to milliseconds. Kalau furnace memang tak dapat lah. So you can go down to milliseconds, high temperature, macam you bagi spike kat dia lah, spike in temperature. Bagi some pulse, a very short time, high temperature, enough to do whatever that you want to get on the device. So that's called RTP process. Rapid thermal processing. General term describing type of process in which temperature of the wafer is rapidly increased by a radiant heating. Usually we use halogen lamp. Halogen lamp kita akan susun in series. Kita akan bagi pulse dia high temperature from high power halogen quartz lamp, right? It's a low thermal budget process useful in several applications in semiconductor device processing in which high temperature exposure is needed but short time. Kalau you pakai furnace, high temperature for quite some time. Then it's going to alter your dopant distribution more significantly in comparison to RTP process. But transfer of the large amount of thermal energy to the wafer is not desired, right? So if you're talking about low technology node, then RTP is a must. If you talk about big technology node, yang besar-besar microns, for example, for automotive applications, where you don't really need to go for nanoscale, gate size, then furnace is more tolerable, right? So that is thermal budget. Let's go back to the slides. Right, so this is so that's basically the essence of thermal budget. So you can see here, it's basically if the diffusion constant at each step are independent of dopant concentration, diffusion coefficient can be written as this. So you can see that it's going to be accumulation of high temperature exposure to the device, right? That will affect your final device properties, right? So when we compare that to a standard diffusion equation with D time independent, we can see that replacing D. So basically this is what influences the thermal budget effects in the device. So consider a series of high temperature processing cycles at dt plus dt plus dt plus dt. So the sum of dt products at the bottom here is sometimes referred to as thermal budget of the process. So you're not inducing dt in diffusion process alone, but rather you have a series of dt in some other processes as well that could also affect your dopant profile without you even know it, right? So for small IC dimension, dopant redistribution has to be minimized, and we need low thermal budget processing, right? So ni schematic illustration of the thermal budget. So you have driving for your diffusion process, and then you will have annealing process as well later on in the subsequent process. So your DT product, your effective DT product is actually the summation of your DT exposure to the device or to the layer or to the channel or whatever, right? That will actually affect the quality of your final device. So not actually during the diffusion process alone. So that's why DT is crucial. All right, so let's get these questions done then. All right, we have like 5, 10, 15 minutes. So have you tried these questions? Let's go through. Right. Question number 1. Boron pre-dep. Okay, the keyword here is pre-dep. So you know already pre-dep is associated with which profile? Either error function or Gaussian. So boron pre-dep step is performed into an N-type substrate at 1000 degrees C. So it's an N-type wafer. Boron solid solubility at 1000 degrees C. So we discussed that your solid solubility of the dopant is dependent on the temperature. So it's known to be 3.5 times 10 to the 20 per cm cube. So that's the maximum level that you can get at 1000 degrees C for boron. And the incorporated boron dose, right, dose Q is 3 times 10 to the 15 per cm squared. So what is the DT product of the pre-dep process? Right, the question is what is the DT product of the pre-dep process? Right, so what do you get? Anyone? What is the DT product? Anyone? Okay, let me call you then. Tak ada volunteer. Well, if you get your result, just write it down there in the chat box. Okay, saya sebut nama saya kira. Nombor 6 siapa nombor 6? 1, 2, saya kira from the list. Saya nombor 1, nombor 2, nombor 3, nombor 4. 9. Yeah. Who's the lucky 6? 1, 2, 3, 4, 5, 6. Go Qingwei, you are the lucky one today. Go Qingwei, what did you get? Can unmute yourself or I can write it down. What is the DT product of the pre-dep process? Qingwei? Anyone would like to share? While waiting for Qingwei. Not done. Okay. Nabila. Nabila dah try? Okay, Nabila, please share. You can write it down ataupun you can unmute yourself. Do 2.34 10 minus 11. 2.3 10 minus 11, right? So how about others? Right? The unit, can you write down the unit as well? Unit jangan lupa, if you write down in task exam, you write the figure to be correct, but the unit is wrong, then you won't have full mark. Ilham 5.8 minus 11. Unit apa Ilham? Write down the unit as well. CM minus 2 ke? Right, how about others? Siapa lagi dah try? Ain 577 10 minus 11 cm squared. Okay, others? Ada lagi yang dah dapat? Tulis je, it's okay. Same answer as Nabila, Shamim, okay. Yeah. So the answer is 5.8 times 10 to the minus 11. 5.8 times 10 to the minus 11. Right. So which equation do we use? Is it Gaussian or error function? Jadi Ain 577, Ilham 5.8, Nabila 2.3. Okay, Ilham, how about you? Do you use Gaussian or error function? Ilham?
Error function.
Error function because? Kenapa pakai error function? Because the process is
Pre-deposition.
Right, because the process is pre-dep, right? So if the process is driving, then it's gonna be Gaussian. So then it's gonna be the pre-dep equation, pre-dep error function equation. Q is equal to 2n naught square root dt over pi, right? Betul, Ilham?
Yes. Yes.
Okay, then you rearrange the dt. So dt is originally on the right hand side, and you can make the dt as the headline. Then it's gonna be pi times q over 2n naught squared. Okay, then your q is known. Q is the dose, 3 times 10 to the 15, 3 times 10 to the 15, and n naught is known. It's the solubility at 1000 degrees C, and that is 3.5 times 10 to the 20. So that will give the dt product of 5.8 times 10 minus 11. Okay, so you just rearrange the dose punya equation. Dose punya equation jadikan dt as your perkara rumus untuk you calculate. So it's 5.8 or 577, sama lah dekat 10 minus 11, right? Done. Straightforward. Okay, let's move on to the next one. So let me reshare again. Okay, question number 2. What is the junction depth xj of the pre-dep, again pre-dep profile, if the n-type substrate has a background concentration of 10 to the 15? So it's 1 times 10 to the 15 per cm cube. Refer to error function graph to get the value. All right. So what's the junction depth then? Right, anyone? Kalau you dapat jawapan, just write down in the box. It's fine. Anyone with junction depth? Nanti saya akan share on e-learn, but let's discuss first. How deep do you get your xj? 9. So since you got 5.8 for your dt, so what is your xj then? Ain Natasha, what is your junction depth? Not sure. Okay, hold on. I'm not sure. Not okay, right? You don't know how to use the function graph. Okay. Siapa yang dah dapat? Anyone? Amirah? Ada dapat? Amirah? Error function graph. So anyone got it? So let me show you. So the equation that you have to use is the equation from error function xj equal to 2 square root dt. So you know your dt already from the question number 1. Error function of of your concentration and not over NB, right? So hold on, let me. Okay, kita go back to the equation. XJ equation. Yeah, right. So error function profile XJ. So you boleh pakai equation number 2 ni. 2 times square root error function N naught over NB. So what is our N naught? What is our N naught in this case? What is our surface concentration? Tadi you dah pakai kan untuk calculation pertama tadi? What is our N naught in this? Surface concentration, surface concentration, and then so that will be your surface concentration, and then NB is your background concentration, 10, 15. So you you over that with your background concentration, and then you come to the, saya tunjuk ya. So it's 2 times square root dt, error function of 3.3 on the graph. So you need to look at 3.3 on the graph. 3.3 is here. Okay, let's show you the my Word file. Word file. Okay, can you see the Word file? Nampak tak? Okay. So this is the graph. So the right hand side is the Gaussian, the left hand side is the error function. So bila you bahagi, you're gonna get the value on the y-axis, and then that will be equal. How do you check that? You have to check check the x value from the curve dekat jawapan yang you dapat bila you bahagi tadi. Then you're gonna get 3.3. You're gonna get about 3.3 somewhere here, right? So you need to plug that equation, and you're gonna get 0.5 micron as your junction depth, right? So 0.5 micron junction depth. So the value that you need to plug in from the error function curve is the value on the x-axis derived from your diffusion process untuk you punya apa ni background dengan you punya surface concentration. I'm going to share this one in the on e-learn later on. So the answer is 0.5 micron. 0.5 micron for your xj. Okay. Right. Oh, if already any questions for today? So we're done with diffusion now. Yeah, we're done with diffusion. On Thursday, we're gonna move on to ion implantation. Right, we're gonna move on to ion implantation. I'm gonna share the slides later on e-learn. Then on Friday is 17, right? Or 18. So on Friday, we're gonna have applied physics alumni in our class to share about his work experience and his background. He's now working as if I'm not mistaken, as a QA engineer in Infineon, Kuliah High Tech. So he's going to share with you just like what we've discussed with Anis Nada last time. Right, so that will be on Friday then. All right, so tak ada soalan? Any questions? All good? Right, if there's no question, then I'll see you Tuesday then. Okay, bye-bye. Thank you. Assalamualaikum.